Hey, thanks for watching. So today I'm going to be doing something a little different. I'm researching diamond in nuclear fusion. At the end of this, I'd like to have basically a PowerPoint explaining nuclear fusion, if you're not sure what that is, why it matters, um, what the methods people are working on to achieve nuclear fusion, and then also in one of the methods to achieve nuclear fusion, inertial confinement fusion, diamond is used as the fuel capsule. And so then I'd like to talk about how it's used, the research, the state of the art, and where things are going to go from here. So let's start a timer so that I can remind myself to come back and check the comments. Then I'm reading here. So first I want to know fission. I don't know what the difference is. Well, I know fission, it's splitting apart. Fusion, it's coming together. But is there more energy released from fusion? Neutron slams into a larger atom, forcing it to excite and split into two smaller atoms. Additional neutrons are also released that can initiate a chain reaction. When each atom splits, a tremendous amount of energy released. Uranium, plutonium, blah, 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 blah. Fusion occurs when two atoms slam together to form a heavier atom. Okay. So here we could say fission, energy. Alright, then let's just go down here. So I've outlined basically what I want to look at. So let's make these headings. And down here. Fission energy. Sorry. This is fusion energy, several times greater than fission. Alright, now why? Why is fusion let's change that to be 15 minutes. Alright, now fusion reactions. If the element is lighter than iron 56 or nickel, Ni, 62. Binding energy per nucleon. Nucleon is either a proton or a neutron. Alright. Large binding energy per nucleon. So it seems like if there was small binding energy, fusion of nuclear lighter than these releases energy, while the fusion of heavier nuclei more energy is released from fusing light atoms into heavier ones than is released from breaking down large elements into smaller ones. That kind of makes sense because it should be easier to break up uranium than helium. I don't know what else to think. Alright, history of fusion pre-diamond. Nice, a Nature paper. Alright, so methods of attaining fusion. First, tokamak, Russian, pinch, high end density, whatever, magnetic Miecha. Stellarator. Blah, blah, blah. I don't care. Alright, so now how does plasma create fusion? Due to collisions with extreme thermal kinetic energies of the particles. If the fusion is confined, particles collide with extreme thermal kinetic energies. Yeah, and then if you just have two hydrogens slamming into each other. I'm not good at the periodic table. So what's helium? Is helium 2 protons and 2 electrons? Two protons, 2 neutrons, and 2 electrons. And a hydrogen's just a proton and electron, right? Yeah. So if you slam 2 hydrogens into each other, you get 2 protons and 2 electrons, and then you need a neutron from somewhere. The fuel is deuterium. Deuterium has an extra electron, or an extra proton, or tritium. Stable isotope of hydrogen. Oh, it just has an extra neutron. And tritium. Does tritium have 2 neutrons? Rare and radioactive isotope of hydrogen. The tritium nucleus contains 1 proton and 2 neutrons. Yeah. Okay, so instead of 2 hydrogens, 2 deuteriums slamming into one another. If they have enough energy, if they have enough kinetic energy. What is thermal kinetic energy? What the hell does that mean? So just thermal energy. If the collision has enough energy, they will fuse to create helium. Then energy will be released. That's a duh. 2 deuterium slamming into each other. If the collision is enough energy, they fuse to create helium. That makes sense. Alright, so back to here. Okay, so is the whole challenge containing plasma? Cold fusion isn't real. Large amounts of energy are released by fusing small nuclei together. Okay, so I don't understand why this releases energy, so let's figure this out. Lighter nuclei are sufficiently small and proton poor. There's not that much of a proton charge in there to allow the nuclear force to overcome the Coulomb force. So the nuclear force, which just holds the particles together. Most commonly observed between protons and neutrons of atoms. Both nucleons are affected by the nuclear force almost identically. Since protons have charge plus 1e, they experience an electric force that tends to push them apart. Yeah? But at short range, the attractive nuclear force is strong enough to overcome the electrostatic force. The nuclear force binds nucleons into atomic nuclei. Releases the extra energy from the net attraction of particles. So it has to do with the nuclear force being short range. So there's a certain amount of energy. Let's go back to deuterium. All right. So, example. 2 deuteriums collide with enough energy to fuse. Alright, so let's call E sub T the total energy holding and then E sub HE is just same thing but helium. Just trying to think, how is that energy released? I mean, okay, so in a deuterium, it's a proton. It's a proton, an electron, and a neutron. You're telling me that the force holding I guess it's that the sum, is it that E sub HE is less than 2 E sub DU? The force holding a proton to a neutron. I don't get why it wouldn't be the same. Nuclei can overcome this electrostatic repulsion. Okay, so that means the electrons are repelling each other. So if there's not enough energy, it goes boing and gets repelled by the electron. However, if there's enough energy, overcomes that repulsion, then the nuclei get close enough so that now there's the attractive nuclear force. Zoop. Why is there energy released? So you overcome the electrons, it fuses, and then the energy released. The energy released is the difference between the energy holding the helium together and the energy 2 times the energy holding a deuterium together. But to me, the energy holding a proton with a neutron times 2, I don't get why that's not the same as the energy holding 2 protons with 2 neutrons. The fusion of 2 hydrogen nuclei to form helium, 0.645% of the mass is carried away as an alpha particle or as electromagnetic radiation. So how's that? releases energy in the mass that always accompanies it. So is that just the you just find the difference in the masses? Alright, so hydrogen mass, let's just do it in AMUs. So deuterium mass is 2. Tritium mass is 3. Helium-4 mass is 4. So basically we have a neutron left over. Why do we get helium-4 plus 3.5 mega electron volts? So it's saying that the 3.5 mega electron volts is the difference between this nuclear force and these nuclear forces. I'm just not getting. Calculating nuclear force holding an atom together. No new chat. Alright, so I'm just confused on this energy. How do we calculate? First off, how do you know that that makes helium-4 and not, I don't know, helium-5? Right? Oh, I guess it just goes to whatever's stable. But where's the 3.5 mega electron volts come from? I gotta reset the timer. Okay. Strong force deuterium. I'm still confused on how do we find... Well, I guess I'm confused. First off, let's make a new section here. Just say random terms. What the hell is binding energy? I mean, the energy binding two things together? What's it mean for something to be unbound? Literally what it sounds like. Alright, what does it mean for a state to be unbound? This seems like some AI thing. Unbound seems like it basically means it falls apart. How does that mean? The strong force grows rapidly once the nuclei are close enough, and the fusing nucleons can essentially fall into each other. I get all of that. Why the hell is that exothermic? Because the final binding energy is less than the initial binding energies. But why is that? If you have a big thing like uranium with a whole bunch of protons, I think in neutrons. There it is. Okay, so a whole bunch of protons and neutrons. Then it takes a lot of force. You gotta overcome that electrostatic force. So obviously that's gonna be bigger. So you need more kinetic energy. The bigger the atom is, the more kinetic energy you need to fuse it, obviously. But then it's something about when the nuclei get close, it's like right here the strong force is affecting some of the protons. Oh, there's the electrostatic force of the protons. Okay, so the strong... I guess it's because the nucleus is too big. You still have the stuff on the other side is pushing, so they can't come together. Oh no, to get them to come together, you need even more energy to put in. And then at some point, they fuse. It's something to do with that. To overcome that electrostatic effect right there, you need more energy. So it's like you need energy to push them past the electrons, but then once they get close enough, it just goes zoop. It gives you some energy back. Is that what it is? It's like it gives you electrostatic energy back? Can we think of it as getting electrostatic energy back when the nuclear force contributes? Two naked nuclei repel one another because of the repulsive electrostatic force. Yeah, that makes sense. If two nuclei can be brought close enough together, however, the electrostatic propulsion can be overcome by the quantum effect in which nuclei can tunnel through Coulomb forces. I haven't taken quantum in forever. Consider two nucleons at a distance, at large, put quotes around it, large distances, the nucleons repel each other. Because of the electrostatic force resulting from the positively charged protons in the nucleus. Alright, and then at close distances, electrostatic repulsion overcome by quantum effect, which tells us nuclei can tunnel through Coulomb forces. So when we're talking about the nuclear force, holds it together. Alright, the key is... Alright, so the nucleons in the interior of a nucleus have more neighboring nucleons than those on the surface. So they're more tightly bound. So if you go like infinite size, the average bounding energy per nucleon, the average bounding energy per nucleon is basically the bounding energy for an interior nucleon. But then when you decrease that, the total bounding energy per nucleon drops. Since smaller nuclei have a larger surface area to volume ratio, the binding energy per nucleon due to the nuclear force generally increases with the size of the nucleus. So that makes perfect sense. Let's put that down. Binding energy per nucleon increases with the size of the nucleus up to 4 nucleons when it hits a limiting value. So a proton added to a nucleus will feel an electrostatic repulsion from all the other protons in the nucleus. The electrostatic energy per nucleon. The electrostatic energy per nucleon due to the electrostatic force thus increases without limit as nuclei atomic number grows. Why would that be? It seems like if you're adding neutrons, then the electrostatic energy per nucleon is going down. Yeah, I don't really get why that would be. The net result of the opposing electrostatic and strong nuclear forces is that the binding energy per nucleon generally increases with increasing size, up to the elements iron and nickel, and then decreases for heavier nuclei, right? And that's because the electrostatic force takes over. Binding energy per nucleon. Eventually the binding energy becomes negative in very heavy nuclei are not stable. The four most tightly bound nuclei in decreasing order of binding energy per nucleon are nickel, iron 58, iron 56, and nickel 60. Doubly magic nucleus. Alright, let's go back up to here. Oh, did I reset the timer? No. Alright. Eventually the binding energy becomes negative. Okay, binding energy, negative binding energy just means this thing wants to break apart. Electrostatic and strong nuclear forces. Oh yeah, okay. Okay. So this is why you can't have an infinite-sized atom. Is because the electrostatic forces take over. So there's some balancing point where we can add a proton. If you just have hydrogen, you have one proton, one neutron. That's the lowest the average binding energy per nucleon can be. Then you add a proton and add another neutron. The binding energy is the same, right? No. You have a higher average binding energy. And a higher... It's like the binding's working against electrostatic. So you start out... Okay, so hydrogen, you start out with only binding forces, no electrostatic force pulling it apart. Then you have helium, where there's all the binding forces between everything in the atom. But you also have the electrostatic forces are trying to rip it apart. And so the total binding energy of helium is less. Yeah, because you have... Oh, okay, so then you have that electrostatic force pulling it apart. Then you go up to some tipping point which happens at nickel 62. Okay, blah, blah, blah. Somewhere around nickel or iron. There we go. Iron 56 or nickel 62. Then it gets to the point where if after iron 56 or nickel 62, if you add another proton, that takes more energy. It takes more energy to overcome that electrostatic force. Oh, what is it? I lost it. Alright, so you're starting with no electrostatic force, just the nuclear binding force in hydrogen. Then in helium, you have the nuclear binding force, but you also have this electrostatic force pulling apart the nucleons. And so the net binding force is less. Add another proton, net binding force is even less. Oh no, forget about the net binding force. Just think about the average binding force per nucleon. So first we start out just that strong, or the nuclear force. Then the average binding force per nucleon is just whatever that nuclear force between two is, divided by 2. Then you get helium, then you get all the nuclear forces are still there, but you also have this electrostatic force pulling apart. So it's because one increases linearly. If you add another proton, then you get, if you look at the average binding force just from the nuclear force, as you keep adding protons, then the average binding force goes up and up and up and up to some limit. It goes up to a limit. Whereas the average electrostatic force, alright, average binding force from the nuclear interaction, zoop, up to a limit. Zoop. Whereas the electrostatic force just increases linearly. Zoop forever. Zoop. I think that's what we're dealing with. And so, if you look at them, there's some trade-off point where now instead of, if adding an extra electron, instead of getting energy back, why are we getting energy back when we make helium? Well, it's because helium has less binding force than hydrogen. So it's at iron 56 or nickel 62. It's like at that point, you try to merge them together, but you have all this electrostatic force you need to overcome. And so at some point, that electrostatic force you need to overcome just becomes too great. And then you need to pour energy in just to get it to happen. Right? When you start out with no electrostatic force in the initial things, then boom, the final thing has some electrostatic force trying to tear it apart, then the total binding energy is less, and boom, you get energy out. Okay, I think that's it. All the protons in one nucleus repel all the protons in the other. Not until the two nuclei actually come close enough for long enough so the strong attractive nuclear force can take over and overcome the repulsive electrostatic force. This can also be described as the nuclei overcoming the so-called Coulomb barrier. The kinetic energy to achieve this can be lower than the barrier itself because of quantum tunneling. Is that the key? Kinetic energy to overcome the barrier can be lower than the barrier? Alright, so it is all about plasma. Alright, so back to it. Let me listen to some music. Z pinch. Okay. Alright, so we got a good idea of Fusion. Let's start a PowerPoint. What's plutonium? What's the abbreviation for plutonium? That's nice. PU. Mm-hmm. Not worth it. Things change, rearrange, so do I. Alright, now we have to credit those with my brown head in Chewbacca. Things change, rearrange, and so do I. Alright, so what did we say the nuclear force does? Nucleon, some component of an atomic nucleus. Alright, so this we should talk about stability and energy. So the nuclear force holds things together. It acts at small distances. Alright, so no effect greater than, what was that, 2.5 femtometers? Then let's put a little note. Alright, nuclear forces, stability, and energy. 1 FM equal to 1 let's make this an equation. Alright. Let's check. Any comments to reply to? Nope. Alright, 1 femtometer is 10 to the minus 15 meters. So the nuclear force has no effect above 2.5 femtometers. So this is a very short range effect. Powerfully attractive. Let's see, nuclear force by distance. Fermi is units of distance. Aha. What's a femtometer? Okay, so a Fermi is a femtometer.
Are your kids in grades 6 to
Hmm. It's not like a single clear photo. Here we go. Okay, whatever. We could. Well, maybe there's something in the Wikipedia. Like it's my last. Like it's my last. Like it's my last. Does that look really bad? Yeah, that looks bad. Whatever. All right. This chart seems not perfect, but whatever. All right. Now the electrostatic force. All right. How do we talk about this? I'ma pour this drink up like it's my last. Like it's my last. I don't know. All right. All right. So in fission, large atoms split apart. Anyway, I forgot to start that timer. Alright, that's it for now. Thanks for watching. Have a good rest of your day.